Learning AI can be tricky. It's tricky because there's so many options. There's so many functions and methods and all different frameworks, and just getting started is a challenge. And something that I really wanted when I was sort of checking out AI was what is like a really good, simple example that I can use as a reference and a starting point that will help me understand how a majority of these frameworks work. And it turns out there is an option. I found my favorite hello world for AI and using a popular framework, or sort of a wrapper, Keras, which allows us to use various backends when training an AI model. By default, it uses TensorFlow, but we don't have to worry about that because we just interact directly with the Keras API. So if you're getting started with AI development, Keras is a really great place to get started because it provides one of the more simple interfaces. Could it be simpler? Yes, it could be a lot simpler. I found one of the easiest ways to get started with AI and actually building an example that really works. Of course, the challenge with AI is that it's so complex and there's a lot of options available, and they all kind of work, which is a little bit of a problem because how do you know which one to choose? At least we can have an example that gets us started with Keras and something that is called XOR gate with Keras. So in computer science, there are different machine operators that you can use when comparing bits. This is necessary for flow control, as when something is a true value, you might want to say this flag is true, so I need to execute and move forward. Or if it's not true, then I need to not do a thing. And so that's a fairly common computer operation. And so what we can do is we can train an AI that learns how to process one of those logic gates. And this is my favorite hello world because it's so simple. You can see it's all on one screen here. Just one giant screen. So for example, we could be using a variety of frameworks. PyTorch is another very popular one, though that one by default requires extra code, and something that I like in general is having very little amount of code in order to achieve the most of my outcomes that I'm looking for. And Keras helps me get there a lot quicker. It's a higher level API that sits on top of those lower level libraries like TensorFlow and PyTorch, or well, libtorch in this case, right? So the C-based library that can communicate with various hardware components such as your CPU, GPU, and other FPGAs or TPUs with Google, for example. Because getting started with AI is so challenging, one of the things that I really wanted was a really simple example, and it took me a while to find one that I really liked. And I've got one for you, and we're gonna walk through it right now. This is called the XOR Hello World. It's like a hello world, but using the simplest AI approach that I could find. There could be something simpler, but let's walk through it. All right, so we're gonna use Keras. We're importing Keras, which is a high-level library that sits on top of TensorFlow or libtorch. We use NumPy, which is a nice sort of a matrix, or it's a nice framework in Python that allows us to manipulate sets of data. It reduces our need to write extra code because it does iterations for us, so we don't need to write for loops or range loops. Okay, and then from our libraries here, Keras, we're going to be using two different kind of layers in our model. One is the dense, which is just a simple matrix. A simple matrix. So just imagine a matrix with a bunch of numbers in it. And we'll be using the default initialization, which I assume are random numbers. So when you create the matrix, when you instantiate the dense matrix, it's going to be just random floating point numbers. And activation is sort of like I would call it maybe in this case, a guardrail. I like to think of it as a guardrails approach, because as you're training an AI and you're modifying those floating point numbers in the matrix, sometimes those numbers can shoot really high, which is a problem, right? Because then you'll have an exploded gradient, or you could have the opposite effect, a collapsed gradient, and it's unrecoverable because the numbers get to infinity. So one way to fix that is use an activation function, which sort of creates a bounds, which tanh and sigmoid functions do for us. They keep numbers within, tanh keeps numbers within -0 or -1 and +1. So even if you were training and the value that needs to be put into the matrix would be very big, like say 100 or 1,000, the tanh function would sort of tamp that down into, a 0.99987 in that range. There are other approaches that we could use that don't require activations, but it's just a lot easier to use them. So we'll go with that. There's also an optimizer, which is going to tell us how we're going to be training the model. Like, what is the approach that we're taking? So SGD is stochastic gradient descent. What that's going to do is describe what we're going to feed into the model in what order, which in that case, stochastic, which just means random. So stochastic is just random. And what that does is it tells, during the training process, which of our inputs and labels are going to be trained on in a random order. Otherwise, you could do it sequentially, so you can train on each one of these inputs sequentially. For example, you do the first one, then you do the second one, and you do the third one, and you do the fourth one, and then you start over, and then you do them over and over. Brings with it a problem. You could have some overfitting or some. Really, the idea is you want to create an AI model that has a general knowledge to be able to see things in the future that it wasn't necessarily trained on, but can give you a really good output answer that has a really high accuracy. Here's where the magic is: the training data. We've got these first two rows here, the X and Y, which is going to be describing details of the features and the labels, which is basically saying the input, the features, and what the output is that you want to train the model to be able to repeat in the future, and that's the Y, or the labels. So we got the Y column, the Y here, which is the labels, which is the output. The target, it's also called the target. It's like, I want you to optimize to get this answer based on the input that I'm giving you. And you can see I've aligned it here in the XY columns, so that way you can see what every iteration is going to occur. So with the XOR operator, when you've got when you're comparing two Boolean values, you've got true or false. When you compare the two with an XOR operator, if both of the Boolean values are the same, you're going to get a false. But if either of them are different, in this case, like one side is true, the other side is false, the output's going to be true in this case. So that's what an XOR operator does, and that's what we want to train an AI to accomplish. We want it to learn how to operate with this gate. We could do the inverse as well and train it on an OR logic gate, and you would just change these input values to match what those outputs would be based on the true or false in those scenarios. We can do the same with an AND gate, but this is just like the simple example, right? We can go further, and you might have a new kind of operator that has a whole bunch of other features. That's where the power of AI comes in, is it's basically you train it to do something, and it will perform that task going forward. When we're creating our AI model for deep learning neural networks, we're able to define what that model looks like. And there's a lot of options. However, there's a general purpose approach that typically works for most of the cases, and is used in all the modern, most advanced AI applications today. So we're going to look at this section here where we're creating our Keras model. So we're going to create a model which is this sequential, which essentially means that it's going to follow step by step based on how you've added your layers. And we've made it fairly simple and fairly straightforward, because we only have a few matrices that we've defined here. So our first layer is going to be our input layer matrix that's going to accept 2 parameter input size, right? So we're looking at it here. So we look at our X up here at the top. Each of these data points only has 2 values in them. So that's going to be our input dimension. And then the first parameter here, where I've set it to 4, just tells you how many units are going to be in the matrix. In this case, I said 4, so for every row there should be 4 entries. So it's like 4 floating point values. So it's pretty small. A pretty small matrix, something that you could easily draw on a whiteboard. And then you see here we have a second dense layer with a value of 1. So that will be 1 floating point value. And that matches our output, which is going to be our target, right? What we want the AI to give us an answer for. The activations are going to be the guardrails that help us guide towards the answer without exploding our gradient in the matrix. We like nice, smooth matrices and not exploded or collapsed matrices. As we get into bigger models and other challenges, even though these activations help us a lot, you can also get into a vanishing gradient problem where it gets a little too smooth, or all the information is stacked over on one side. And so that's one of the general challenges with AI. When you're building a model, you need to make sure that that matrix stays smooth. You want it a nice gradient, and it has as much information and detail spread out. Otherwise, a large majority of all the knowledge information will start getting packed over into one side of the matrix, which means it's the vanishing gradient problem, and you'll run out of room for the AI to learn any further. One of the hacks is just to increase the number of units, but that increases the cost of compute as well. And if you get too big, then the computer just doesn't have enough memory. So there's no way for it to even process that. When we're training an AI model, there's a lot of approaches that you can take. The most common industry standard is backpropagation, which is how we learn as humans too. We are asked a question and we don't know the answer, right? So say we're asked a general question like 1 + 1, and say we didn't know math yet. We don't know math yet. We don't know that the answer is 2. We don't even know the answer is a number. So we might say Z. And in that case, then which is a very wrong answer, but it's totally fine. And so what we do is we go back and say, okay, you're on the right track because there's an answer there. However, it's closer to this number here. And so you can do the same thing with AI training as that's what we do when we're doing backpropagation. We ask the AI, hey, what do you think the answer is based on this input data, 1 + 1, for example. And then it spits out a random answer and it's like, no, that's not right. Here's the right answer. And then what we do is we make slow corrections to it. We don't jump immediately to the answer because you could, you could, but if you did that, you'd have an overfitting problem. And so the AI would be, you could train it to do that. If you really wanted to, you could train an AI and you do it in one step and it would immediately know the answer. The problem is though, then if you start asking it other questions, it will get those wrong more often. And so what we want to do is create a general purpose AI that's able to answer questions correctly that it's never seen before. And so when we're training an AI, stochastic gradient descent, the random gradient descent, was we put the data in at the top of the AI, it gives us an answer, the wrong answer, and then we say, okay, how far off is that answer from the real answer based on its matrix. And what we can do is we use a MSE for the loss function, mean squared error, which basically just an average of all the matrices value based on the delta from the answer. So like say if we did 1 + 1 and it answered 10, but the answer is actually 2, then imagine it's like off by 8. So then we take that off by 8 using the learning rate here, which is 2% in this case, and which will ever so slightly say, okay, you're very close. You're not close at all. Here, just modify your matrices by 2% of the amount that you were incorrect. And then what we do is we do that over and over and over again, and eventually a matrix will form in a nice fashion that will always give us the right answer. That's AI, that's training. Overfitting is a common challenge with AI. When we're training a model, depending on what you've trained it to do, can get really good at what you've trained it to do, but then perform poorly on tasks that it should be able to do that on data it's never seen, and it will give you wrong answers. Thus, a typical overfitting problem where it's used all of its matrices and all of its floating point values to learn exactly what you've trained it, but then when you put in new data it's never seen before, it gets pretty wrong answers. And so there's tricks and patterns and strategies to reduce overfitting. And one of them is by randomizing the order in which it's trained from its input data. Stochastic gradient descent, which is the randomization of all your training data. So we've got all of our input data here at the top, which are our features or labels or our input data. And then we've got our output data here, which is the targets, right, of the correct answers. This is also called the labels. And what stochastic gradient descent will do is just randomize the order in which things are trained. So you'll get a less overfitting. That's just one strategy. There's more. You can also change the learning rate here. For example, I've set it at 2%. You can reduce it, or you could change it over time, so that way the learning rate might jump or sure, because there's a problem of local minimum where you can get an answer that gets stuck in a gradient, but it can't get to a better answer or a more generalized answer if it was able to jump out. And so if you change your learning rate during various cycles, you can also reduce the overfitting problem. Ooh, another one is you can change your batch size. So batch size is how many of these inputs when you're training the model are you going to process in one go. So you can include like 3 or 4 or all of these options, because there's only 4 options here, but you can include all these options and you can randomize them, and you can do a matrix multiplication against them and get your output answer, and then run the mean squared error across all of those. So now you've got a pool, and even though it had 4 different answers, you can run an optimizer that buckets all of that together and creates a loss based on how far off. So maybe one of the answers was really far off, like it was just way in the left field, but the other 3 were pretty close. So that one answer, because it was so far off, will allow us to adjust our matrices in another way so it's more balanced. And that's why batching is really important. There's also other benefits of batching when we're submitting work to a GPU because of the time latency in the hardware. So from a training time perspective, that could also help. But batching is also really powerful if you want to increase your batch size to reduce your overall overfitting. So that's 3 really good, powerful capabilities just right there, all in this hello world. It really simple, just 29 lines of code here. And we're already employing 3 powerful strategies that reduce overfitting. Okay, now we're going to train an AI, or an actual AI that does a thing, and it really works, and it's really simple, and it's really powerful, and it works really quick-ish, right? So what we have here on the screen is a full end-to-end, just 29 lines of code here that will train a model to perform one of a common operator, the XOR operator, which compares 2 Boolean values and gives you an output. So we've got our input and output data here. So our target data, which is the Y, the labels, and the features are the input data. And so what we can do is we can train our model by running the fit function. In Keras, it's called the fit. It makes sense because what we're doing is we're sort of optimizing and making sure that the input data and the output data can match in a way. So fit is kind of a nice way to, I would say, but you could also call this like it's fit model, or it's like, I would say train. It's like training the model. You're training the AI. This is the machine learning part. Once the model is trained, you can then use that model going forward to give you all the answers for any future data that you provide it. And it will always do the work for you, which is the nice part about AI, is you just train the computer, and then going forward, it will do everything for you. It doesn't do it right, you can always retrain it, or you can add to it later. You don't have to retrain the entire thing. You can always just modify it again and then keep doing that process. So over time, you can continuously train a model, and it can get smarter over time. It's so cool. All right, let's open up a new window here and then run some. We'll run it. We'll actually train the model. Here it goes. All right, so what it's doing now is it's running through all of our data, and then it's feeding through the model, and then it's optimizing. Oh, it is done. Okay, so it's completely trained. It only took a few moments there. Okay, so what we're doing is we're looking at this output here, line 28 through 30. And in this case, we see our output model is predicting, we're doing 100% of the data just to see what that looks like. And then the answers came out like this. Now you can see their floating point values. However, check it out, as we're doing training, we want to, ever so slightly modify the AI or the matrix, so that way it gives us the right answer, but we don't want to get it to 100% all there. I mean, we could. There are use cases for that, but in this case, we're using this is deep learning here. So we've got multiple layers of matrices. We're backpropagating to them, and we're slowly modifying all the matrices so that way it gets closer and closer to our right answer. And as you can see here, even though it's at 0.8, it's actually very close to the perfect answer. And this value should be 1, right? 1, 1, and then 0, 0. And so you can see that there is a nice delta between them, and it's good enough to where we can say there's a threshold. So we'll say if anything above 0.5, that's going to be 1 or true, right? Anything below 0.5 is going to be false or 0. And so when we run the NumPy round function, that's exactly what that's doing. And then it gets us our final answers here. So we're able to get that data, and it will fit on either side by running the round function. And this is the common process. And you also have like things like softmax, which will give you, you don't actually have to run do you have to run softmax? Softmax, if you're familiar with softmax, it just takes the entire array of outputs, right? So something like this, where the answers on the outputs could be like wildly large numbers on all sides, and then it tamps them all down into a nice even range between 1 and 0. Right? So that way then you can sort and find the best items in that case, which is a different use case altogether. But look, we did it. We trained a model. We got it to work, and it only took moments. And this is even running on GPU hardware. It's just running on regular CPU. And there's many like knobs and dials to turn. So we've got your batch size. You can increase the batch size to go bigger. You can do more training sessions. Each epoch is representative. The word epoch it's defined as a large amount of time. No specific units, just a large amount of time. And in an epoch in AI world is where it's one epoch is equal to running 100% of your training data set through the model. So if you have 1,000 training data points, an epoch will elapse once all 1,000 have been run through the first time. And so when you want to do more than one epoch, slowly train the model and repeat the same information again. And so 2 epochs will be identical to repeating every single training data point twice. So in our model here, we have 4 data training points. In this case, there's 4 data training points. And with this 4 data training points, that would be, each epoch would be 4 cycles. Well, in this, if the batch was 2, then that would divide that in half. So that would mean two backwards propagations in that case. So that would be overall as an operation of 2,000 overall operations from that perspective. But if we reduce this to 1, then that would be 4,000 epochs, or 4,000 data cycles. So we did it. We made it happen. All the AI is done. It's right there on the screen. And now what you can do is you can take this approach and then modify it. You can put different input data here. You can do different output data. You can change some of these hyperparameters, and you can run and retrain. You can use a different loss function. You can use a different optimizer. There's so many options, but what's really important here is that we have a good working example that you can use to get started from. This is something I really, really wanted when I was getting into AI, and it didn't fully exist, or it wasn't easily obvious that this was a good path to get started. And I thought this was my favorite. Once I ran into this, most of the AI stuff started becoming more accessible.